fractions. So let's just make sure we're still remembering how to do these. There we go. So order of ops would have us do the multiplication before we do the addition. And so my first step would look like this: negative 2/3 plus 1/10. Look okay? And then my next step would be to add. And in order to add, I need to have a common denominator. What would you guys say would be the common denominator between 3 and 10? 30. There we go. So it's going to be, let's see, it would be negative 20/30 plus, morning, glad you made it, 3/30. And so then when you add these up, you would get negative 18, or negative 17, excuse me, negative 17/30. I do not believe that that reduces, and so we would stop right there. You guys doing okay with number one? Old but good still? Yes? No? Good? Okay, cool. All right, and then number two is a simplify. Good morning. Glad you're here. Do you guys do the distributive property before you do anything else? Okay. So the 3 would get distributed, and so we would get 12x squared minus 6x plus 15. And then the minus sign also gets distributed. So that would be minus 5x squared minus 3. Doing okay? And then you'd add your like terms. What is like 12x squared?
Negative 5x squared.
That's right. We keep the sign in front of the number with it, so minus 5x squared. When I combine those, I get 7x squared. Tell me, please, what is like minus 6x? Nothing. So that just gets put into our answer. And then what remains there, the 15 and the negative 3 are like terms. Added together, those give you 12. So that would be my final expression. Still doing okay? Okay, so I'm hoping number 1 and 2, other than maybe just like a silly error, were fairly simple for you. Do you have any questions, though? I mean, because they are old, and that's kind of why we're doing these, right? It's easy to forget things that are way in the past. So any questions about anything I did up there? All right, so then number 3 takes it up a notch as far as the challenge goes. It says John went for a hike. The temperature at the trailhead was 60 degrees Fahrenheit. At the summit of the mountain, the temperature was 38 degrees Fahrenheit. The trailhead elevation was 8,500 feet. The elevation at the summit was 14,100 feet. Write an equation in slope-intercept form that shows the relationship between the temperature and the elevation. So how many of you used y's and x's to help you express this? So nobody did. What did you use? What? Or did we get nowhere with this one? Say again?
T and E.
T and E, temperature and elevation. Is that what you guys use? Only got half of it? But I'm not asking what your answer was. I'm just asking, did you use y's and x's, or did you try to use y's and x's, or did you try to use t's and e's, or something else?
Yeah, I really chose to.
You did what?
I used T's and E's.
T's and e's. Anybody use anything different? Okay, fair enough. So we're going to use t's and e's. The way this is stated, it says, write an equation in slope-intercept form that shows the relationship between temperature and elevation. So here's what that means. That means if we're going to use t's and e's instead of y's and x's, this would look like in the end t equals me plus b. Right? So like the e is in place of x, the t is in place of y. You could also use y equals mx plus b. Good morning. But we can use this for sure. Okay, the order is very important. T is depending on E, and so it needs to be T equals ME plus B, not E equals MT plus B. That make sense? Temperature depends on elevation. Okay, so the first thing we got to have here is a couple of pieces of information that will help us get this. So what are the two things you got to have to write the equation or the graph of a line?
Slope and a pointing line.
slope and a point on the line. So, all right, so I've got my slope right here. I don't know what it is yet. And I also need a point. So let's see here. Any idea on how I could find the slope? Yes, ma'am.
It'd be T1, or I mean T2 minus T1 over U2 minus U2.
Stop and look what Kyrie wrote, or what she said and what I wrote. This is really well done. Why did you put the T in the top?
Because it stands for Y.
Yeah, T's the output. That's right. So the change in T goes in the top. The change in E goes down there in the denominator. It's well said. Okay, so then let's keep going with this. Sorry, I wrote that in the wrong spot. Let's just switch this around. This is my slope, and my point I'll put up here. Okay, so what's my second temperature? What's that T2? Say 38? 38, agreed. So minus my first temperature then would have to be 60. Which elevation goes with 38? 14,100, so that goes down here. And then which one is the other elevation that goes with the 60? 8,500, yep. Okay. So this is going to be my slope. So 38 minus 60 is negative 22, and 14,100 minus 8,500 would be 5,600, I think?
Yeah.
5,600? Okay. Did anybody try that out and it reduced? I mean, obviously I can see they're both divisible by 2, but by any chance does 22 go into 5,600 evenly? You try that out real quick for me there, Ben? No? Okay, fair enough. All right, so negative 22 over 5,600 is my slope. Any ideas on a point that I could use here? Got to have a slope and a point.
You could use 60 and 8,500, or you could use 38 and 14,100.
Okay, so let's just use the first one you suggested, just because, right? So right there. So 60 and 8,500. What would be the ordering on my point? It's got to be something, comma, something, and of course the order matters. Would it be 60, comma, 8,500, or 8,500, comma, 60?
8,500.
Why?
Elevation.
The elevation goes with X, that's right. So 8,500, comma, 60 would go here. Okay, so we'll see how these numbers work out. We're supposed to write this in slope-intercept form. I'm going to start off with point slope because that's what I've got. So I'm going to write T minus 60 equals negative 22 over 5,600 times E minus 8,500. Does that make sense? Point slope using T's and E's. All right, so this would be the time when you definitely would want to break out the calculator. We need to do a little distributive property, and we need to add the 60 over and all that stuff. So I will quietly sort of put this together up here, and we can check our answers. You can help me at least here in just a second. Yes. Bless you. So I think I've got an answer up there. You guys agree with I do my arithmetic right? 93.393 for the y-intercept? Yeah? You good with that? Okay. All right. So, yeah, questions? What do you think about that one? For those that came in a little bit late, mentioned we're going to do this DMR for quite a while. We're going to do this DMR throughout this week and throughout the week when you come back from Thanksgiving break, and we'll finally do our DMR quiz at the end of that week. So you'll get a lot of chances to practice this. Okay. Any questions at all? Okay. So here's what we're going to do. I want to discuss number 4 real briefly. Here it is. And I'm going to give you a chance to kind of read this over and hopefully come to a place of like, oh boy, I am not sure I know what to do with this. We're going to come all the way back around to this at the end, and hopefully it'll all make sense, or maybe a little bit more sense. Good morning, Jaden. So let's read this over really quick, and then we're actually going to jump into our lesson. Like I said, we'll come back around to this. So this says, Abby leaves her house in Highlands Ranch for the mountains on Friday at 5 p.m. She drives an average of 50 miles per hour. Her sister, Candace, leaves the house at 6 p.m. She drives an average of 70 miles per hour. The mountain house is 220 miles away. Will Candace catch up to her sister? Show your work. If she does, at what time does she catch up to her? Whew. There's a lot going on here, right? So, Joe, did you have are you just stretching? Just stretching. Okay, continue to stretch. I won't call on you. So I think what we need to do with this, I think we need to look at some other aspects of this sort of question. We'll come back around to it at the end, okay? So maybe you've noticed this, but for most of this particular concept here, actually for all of it for the next couple of days here, I have 2 examples each day. There's 1, there's 2. There's 1, there's 2, and that would be it. It's actually pretty short, but we're going to take plenty of time with each one of these. Before we get rolling with this, I wanted to talk to you guys a little bit about your week this week. So don't worry about this right this second. Monday, Tuesday, Wednesday, Thursday. So here's what we're going to do. This week, Monday, which is today, of course, we're going to be working on this application of linear equations, D equals RT. Okay? Tuesday, we're going to be working on D equals RT. Okay? So like the whole class period today and tomorrow. Wednesday, we are going to have, I believe it's Wednesday, we're going to have concept quiz 10, which is our final concept quiz. This will be over the applications we've been looking at with linear equations, like rates of change, percentages, and some of this stuff as well. And then on Wednesday is when we start our project, our final Unit 3 project. And Thursday is also Unit 3 project. And that'll actually be for our regular classes for the rest of the semester, will be the Unit 3 project. If you're on task and doing well, Unit 3 project should be able to be done like 99% of it right here in this classroom. It shouldn't be anything that you have to take work home for. Of course, if you're unproductive or choose to, you could, end up doing stuff at home. But the intent of it is to give you lots of time here in class to work together to complete that Unit 3 project. And you'll find out about that on Wednesday. Okay? Question? No? Okay. So we'll continue with that Unit 3 project on the other side of Thanksgiving break for like 7 or 8 days, something like that, 5 or 6 days. And we'll eventually get to our Unit 3 test. And by the time that rolls around, we'll almost be at the end of the semester and Christmas break and all that stuff. Okay? You good? All right, so let's take a look here. Have you guys ever seen questions like this before? Like the one I just read to you, or this one right here? So I have a way that I like to show you. There are other ways, and if you're struggling, we could approach this as if it's a system of equations. We can approach this from a non-systems perspective. We can use a graphic organizer. We can not use a graphic organizer. There are a lot of different things that we can use. But the one thing I think we need to make sure that we don't get away from is that this is simply a story. And for most stories, you can draw a picture representing the story. And that's going to be the first thing we do. We're not going to get worried about the math. We're not going to get worried about anything. We're not going to get worried about the relationship, D equals RT, which we'll talk about here in a second. We're simply going to look at this and be like, whoa, it's a story. I need to draw a picture, and I've sort of kind of drawn a picture for you. We're going to draw our own little picture. So let's read this one right here. Number 1. So do this with me. Don't just sit and watch. You need to put pencil to paper and see how this works out for you. So number 1, car leaves Rockford traveling towards Wausau or whatever that is at the rate of 55 miles per hour. At the same time, another car leaves Wausau traveling toward Rockford at the rate of 50 miles per hour. How long will it take them to meet if the cities are 157.5 miles apart? So even before we draw a picture, I read it out loud. I hope you read it with me. Can anybody just sort of describe in like a very brief couple of words, like what's happening here? Joe? Well, you're getting way far ahead of me. So like you're starting to do the math. You're like proportions and algebra, and like we'll get to that stuff. Right now, I don't care at all about that. All I care about is tell me about just the story. Not too worried about any of the big details or how to do this yet. I just want to hear a story.
Two cars heading from different cities towards the same city at different speeds.
Heading towards
Each other.
There we go. Say what you said again.
So two cars from different cities heading towards each other to the other city at different speeds.
At different speeds, right. And that's even, like the at different speeds, I mean, that's very true, but I don't think we need that at this point. Basically, isn't it, she said it really well at the start, two cars from different cities heading towards each other. Do you think you could draw a picture of that? Like just using really basic symbols like arrows and dots and stuff? You think you could do that? Try it. Ready, go. Draw a picture, literally. Take your pencil and please don't write really, really huge, because I've given you a lot of space here, but don't like write smack in the middle of your page. Draw the picture. Like draw it near the top. So you have plenty of room to do the stuff you got to do. I'll try to do the same. Let's check our pictures against each other. Good morning. Okay, look at my picture and look at yours. How we doing? Is this the basic plot? I really think your picture should look something like that. I mean, yours is way nicer than mine, but we have the same basic idea, right? Okay, and yours is also nicer than mine. Okay.
Well, you have to do one of them like an arrow longer than the other one because they're going different.
So here is, can I give you guys some temptations, some common errors here? One of the most common errors is to make a quick judgment. Listen, please. I'm about to tell you what some people do wrong. I would think you'd want to know this. This is what some people do that's wrong. They're going to look at this and be like, oh, this is easy. If I just take 157.5, use my calculator, and divide it by 2, this will give me the right answer, won't it? It'll tell me how far they've gone to, what's so wrong with that?
They're going different speeds.
They're going different speeds. So I try to sort of represent this up there, like my blue car. I try to make that arrow a bit longer than the green car's arrow, indicating that one car is going to go for a longer distance than the other one, right? Because one's going faster than the other. So we can't just do that. It's never going to be that simple in a case like this where the cars are going different rates. So are you guys okay with that aspect of the picture? Okay. So now let's build this picture out a little bit more. Is there anything else about the distances? I don't really care about speed right now. I don't really care about time right now. I care about distances. Is there anything else about a distance that I could put up there?
It's 157.5 miles.
That's right, and that's very important. So couldn't I represent the entire distance with 157.5? I think you want to put this in your picture too. So if you haven't already put this in your picture, take a minute and let's make it clear that the distance between the cities where these two cars started is 157.5 miles. Okay. You guys still doing all right? Okay. So now, the last thing I'm going to do here, I want to start putting in some variables that'll help me because I'm about to write a really key equation. So I am going to, and this is just how I wrote mine, so I'll just ask that we all use the same kind of variable. So what I'm going to put here above the blue distance, I'm going to put dB for distance of blue car. And on the green distance, I'm going to put D sub G for distance of green car. Does it make sense?
Yes.
Distance of blue car, distance of green car. Okay, so here's going to be the first significant challenge beyond drawing the picture. Can anyone write an equation, a relationship, involving the distances? What would relate them? What would put them all into one statement? Kyrie, what do you think? So she said dB plus dG equals 157.5. What do you think about that? Does that seem accurate? She's saying the distance gone by the blue car
Yes.
plus the distance traveled by the green car would have to equal the total distance between the cities. Does that seem true?
It does.
It's totally true. That's a really good statement. When you write this relationship, guys, there's one requirement for it. It must be true. That's it. So this is not where we're going to just like have this kind of cookie cutter approach where we always do this or we always do that, other than the fact that we're always going to try to write something that is true. The truth is the only requirement. Hopefully it'll be useful as well. Okay? So we've related the distances, and this is where we're going to get into our other relationship. How many of you guys have ever heard the relationship distance equals rate times time? Have you heard this before?
What?
Distance is equal to rate times time. And so this is true of a car traveling, of a person running, of a bicyclist bicycling, or whatever it might be. If you want to know the distance the person has gone or the car has gone, if you know their rate and you know their time, just multiply the rate times the time and you'll get their distance. Okay? So let's fill some stuff in here. Distance of blue car. Do we know the rate of the blue car? 55. Yeah. So a car leaves Rockford traveling towards Wausau at a rate of 55 miles per hour. That's my first car. I'm calling that my blue car. So I'm going to say the rate is 55. Do we have any idea the time that the blue car has gone?
No.
I don't see any hours. I don't see any relationship between the times. So I'm going to say distance of blue car, 55 times time. Right? Distance equals rate times time. I'm simply replacing distance with rate times time. How about the distance of the green car? What's the rate of the green car? 50. And do we know the time?
No.
There is a key reference to time, though. What is that key reference to time?
Oh, yeah.
I don't see anything about hours. Miles has nothing directly to do with time. But the word time is in there.
When they meet?
At the same time.
At the same time and when they'll meet, right? That's the two kind of references to time. So it says at the same time, another car leaves. So didn't they leave at the same time of day? And when will they meet?
The same time.
At the same time of day, right? So those are kind of our key time elements. And so I would say that the T I wrote earlier would be the exact same time as this green car's time. All right, so this equals 157.5. This actually looks like a pretty easy equation for you to solve, doesn't it? Let's add them up. So it'd be 105t, when we simplify the left side, equals 157.5. Dividing both sides by 105. Maybe the calculator would be handy here. 157.5 divided by 105. It actually comes out pretty nice, I think. Did you guys get 1.5?
Yes.
1.5. All right, so T is equal to 1.5 hours. That is how long it will take them to meet.
So D equals.
Does that make sense?
Yeah. It does.
Okay. All right. So I just want to review very briefly what we did. The first thing we did, and I think I think this is the crucial step that often gets overlooked as people attack questions like this, the proverbial word question, is we want to just jump in and start doing math, right? So like early on, Joe was like, hey, I think we should do proportions. And it's like, well, we never really got too hung up on that, right? We approached it like a story. We drew a picture. We started to label our picture. And from our picture and our labels, Kyrie helped us with an equation. Then we used the D equals RT relationship. And things kind of fell nicely into place. So I would encourage you guys, don't force the math, right? Let it be a story. Get the right relationships in place. And then you have the skills to solve equations. I mean, to me, there's very little doubt about that, right? I don't have any question about that. It's just, can you interpret the story correctly? That's kind of the idea. All right. So we need to do another one here. You guys need lots of practice with these. We all do. And so let's take a look at number 2. This one is a slightly different situation with some incredibly engaging graphics. Here we go. A group of rock climbers is traveling the southwest by car. Their gear is carried in a minivan. How long will it take the car, traveling at 60 miles per hour, to overtake the minivan, traveling at 50 miles per hour, if the minivan had a half-hour head start to the next climbing location? So here's what I want you to do. Please take a minute. I want to tell you, this will be different than the one we just did a second ago, but try to draw a picture of this situation. Just read it as a story. Don't get hung up on rates and times and relationships and all that stuff yet. Just simply draw a picture of their distances. Draw a picture of their distances. Label it if you want, but we'll check your picture here in just a second. Essentially, the van gets a head start, right? Jumps the gun a little bit. So I'm going to say, in my picture at least, maybe I'll just draw this up here. I'm going to say the van is out here, and the van is heading that direction. I'll label that in a second. And then because the van kind of got a head start, you'd say the car started a little ways behind the van. So we'll just say like over here somewhere. The key idea is this, that let's try this again. The car is eventually going to catch up to the van, right? Eventually they're going to be at the same spot, right? Car's going to catch up. So maybe something we could fill in, maybe you already did this. How much of a head start did the van get? Like how many miles?
30 minutes.
Well, okay, so we got to be super careful. I just heard 30 minutes. I'm wondering for a distance, though. Like how many miles of a head start did the minivan get?
25.
I think we can figure it out pretty straightforwardly, because if distance equals rate times time, what is the rate of the van? And how long, like how many hours did it get the head start? Half an hour. So I think the distance of head start for the van was 25. So the van went for 25 miles before the car even got going. And so I'm going to say that distance is right here. Right? So that's that head start distance for the van. So the van goes for 25 miles, and then the car starts. Does that make sense? Okay. So I'm going to label this with distance of van, and I'll label this distance of the car. You guys okay with my picture? Your picture looks something like that?
It looks a lot like that.
Beautiful. That's awesome. So, I feel like sometimes people will sort of like, they'll like minimize the importance of drawing a picture and labeling it and all that. I think that's the thing. Like if you can take the words and draw an accurate picture with some labeling, That's what's going to set you apart, is being able to understand and get these sorts of questions versus people that are like, well, I just sat there and stared at it for a while and I never could quite figure it out. I think the staring at it for a while method doesn't ever work that well. So I'm trying to get you in a good place here. All right, so then once we have labeled this, gotten all this stuff, and I want to give you guys a moment to do this. Maybe you've already tried this, but I want to give you a moment to try. Let's write a true relationship regarding the distances. The only requirement is that the thing you write down has to be true. It can't be made up. It can't be false. It can't just be random blah, blah, blah. It's got to be a relationship, which involves an equal sign, and it's got to be true. And just so you know, it will be a different looking relationship than the one we just did, the one with Rockford and Wausau.
No, this is not.
It's got to be true. Josh, sorry, listen up, please.
Maybe DC.
So, Josh, I'm sorry, I'm going to interrupt you one last time. Chase, everybody, please be quiet. Let's see what Josh has to say. I don't know what he's going to say.
I said DC minus 25 equals DV.
Okay, DC minus 25 equals DV. So you guys remember, the only requirement for this relationship is that it must involve the stuff we care about, but it must be true.
Yeah.
Did he write something down that's true? Is that true? Does DC minus 25 really equal DV, or is that false?
That's true. I think.
If you take the distance of the car and you subtract 25 miles off of it, would that be the same as the distance the van traveled?
No, because the van had a head start. No, it's true.
The way we have it labeled up there, it is 100% true. Look at it. This is. Do you see why the picture makes all the difference here? The picture should help you visualize this, because quite literally, like if you take this longer distance and you subtract out this little 25, don't you get the blue distance?
Yeah.
So remember, the only requirement is that you must write down a relationship that is true. There's other ways you could have written this. Did anybody write something a little different that you feel like, yes, mine is also true? What do you think?
I'm not completely sure, but DV plus 25 equals DC.
That, my friend, is 100% true. Do you see how, isn't that just a rearrangement of what Josh suggested?
Yes.
That is also totally true. Callie just approached it from a slightly different angle. She said, hey, shorter distance plus the 25 equals the longer distance. It's the same relationship, just written in a slightly different way. Can anybody think of a third way you could have written this? Joe?
Correct me if I'm wrong, but I wrote x divided by,
Well, no, hold on. You just said X. Now I'm feeling lost.
so x is like the total distance.
Okay, so that we have to define our variable. So Joe says X equals total distance. Keep going.
So x divided by 60, 10, which is 60 miles per hour,
Okay.
is equal to x divided by 50n minus 30h, which is the slide.
What the?
Whew. So Joe, I think what you have fallen victim here to is you are trying to you're trying really hard, and I think you have some elements sort of in place here, but you're trying so hard to over math this, and I would encourage you not to. Like you're getting into kind of the proportion thing, right? I don't think that's going to work very well, because and I don't know if you learned that in maybe a different class. The 25 thing is going to throw your proportions completely off. I would encourage you to do it this way. I really honestly would. So the x over 60, if that's the total distance, would that be the total distance of the van or the car or both?
It's the x over 60 would be the total, no, the x over 60 would equal the total distance of the purple part, so D1.
But then you're setting up the x. I think I sort of see where you're going with it. But so distance over rate would give you a time, but then 30h is not a time. You're mixing them up.
Okay.
I don't think that one's going to work. Is it okay for me just to say it that way? I just don't think it's going to work. Okay. And again, at this stage, we should only. I really think we should only be writing stuff about distance. In just a second, we'll get into the R's and the T's and all that stuff. But I think I would label distance with the letter D. I don't think I'd mess around with X's or anything like that. I want to know that distance is D, R is rate, T is time. When I start throwing X's and Y's in here, I'm just like, wait a minute, what did X stand for? That was distance, but last time it was rate, and now I feel lost. Oh, and the other time it was time. Now I feel even more lost. I'm going to use D's, R's, and T's because I know what those mean. Okay. Well, how about this? What if, I was going to write another relationship. I think what we have up there is really, really good. I'm going to stick with the first one simply because it was the first one, although I must say that Callie's would work just fine. So we got this right here. I need to remember that distance equals rate times time. So what's the rate of the car?
Oh, 60 miles.
60 miles per hour. And isn't the time that the car went an unknown? So I'm going to put 60 times t. T for time. So 60t is the distance of the car minus 25. Now the distance of the van would be rate times time. What's the rate of the van? 50. And what's the time of the van? It's an unknown. So we get to here. And simply, guys, the idea is that if you have followed each of these little steps along the way, you should hopefully get to an equation that for you guys, since you practice this so much, get to an equation that's really easy for you to solve. That would be the hope. What would I do first if I was going to try to solve this equation? Okay, subtract 60t makes sense. So if I subtract 60t, I get negative 25 equals negative 10t. And then divide by negative 10. So it's going to take the car 2.5 hours to catch up to the thing. One word of encouragement here for you. I know as I walked around, there were some folks that they saw the half-hour head start thing, and they were using 30 to represent half hour. Be super careful with that because 30 is not measured in hours. It's measured in minutes. You want to be consistent with your units. If you've got like miles per hour and miles per hour, and then you decide to use minutes, you're going to have an issue with your units. Okay? So we're coming up here towards the end of our class. What I would like you guys to do is rewind a little bit. Go back to the DMR, and I want you to read over that DMR question again. And at the very least here, I want to see if maybe now this makes a tiny bit more sense. You might not have it mastered yet. That's where we're going to spend a lot of time with this. But I'm hoping that you'd look at this and be like, oh, there's some stuff I could do. So take a minute here, take a couple of minutes, and see. We just have like 2-3 minutes left in our class. See if you could start to get this set up. See if you can identify sort of the type of question, get a picture drawn, start labeling it. See how far you can get. Maybe tomorrow at the start we'll check your answers. Maybe review it and check your answers.